Good day everyone. My name is Mahid Mangontarum from the Mindanao State University main campus in Marawi City. Today, we are going to discuss NP-complete problems. Computational complexity theory is a field that focuses on classifying computational problems according to their resource usage and relating these classes to each other. These usually employ the use of computers or mechanical application of mathematical steps such as algorithms. In this field, a problem is said to be NP-complete when a brute force search algorithm can solve it and the correctness of each solution can be verified quickly. NP-complete problems can also be used to simulate any other problem with similar solvability. The name NP-complete is short for Nondeterministic Polynomial-time complete, where nondeterministic refers to nondeterministic Turing machines, which is a way of mathematically formalizing the idea of a brute force search algorithm. On the other hand, the term polynomial time refers to an amount of time that is considered quick for a deterministic algorithm to check a single solution or for a non-deterministic Turing machine to perform the whole search. Lastly, the term complete refers to the property of being able to simulate everything in the same complexity class. This basically means that a problem for which no efficient algorithm is known is considered to be an NP-complete problem. If a problem is considered NP-complete, then it cannot be solved by any known polynomial algorithm. Should there be a polynomial algorithm for any NP-complete problem, it would mean that there is a polynomial algorithm for all NP-complete problems. Based on those two properties, there is a conjecture that states that no polynomial algorithm exists for any NP-complete problem. However, it is important to note that being a conjecture implies that it has yet to be proved. Apparently, any algorithm that claims to correctly solve NP-complete problems would require an exponential amount of time. Hence, it would be impractical for all but very few instances. Once a problem is identified to be NP-complete, one is generally willing to settle for less ambitious goals than developing an algorithm and may choose one of several possible alternative approaches to the problem. Van Leeuwen in 1998 formally defined an NP-complete problem to be a decision problem C satisfying the following conditions. Number 1, the problem C is in non-deterministic polynomial time. Number 2, every problem that is in NP is reducible to C in polynomial time. In this definition, problem C can be shown to be in NP by demonstrating that a candidate solution to C can be verified in polynomial time. In another paper, Van Leeuwen noted that every problem satisfying condition 2 is said to be NP-hard whether or not it satisfies condition 1. Lastly, a consequence of this definition is that if we had a polynomial time algorithm for C, we could solve all problems in NP in polynomial time. This is consistent with property 2 presented earlier. The easiest way to prove that a problem is NP-complete is to first prove that it is NP and then reduce some known NP-complete problem to it. It is therefore useful to know a variety of NP-complete problems. The following is a list of some well-known problems that are NP-complete when expressed as decision problems. Notice that the problem of assigning colors to vertices, edges, or faces of graphs that we have discussed in an earlier video is an example of an NP-complete problem. Presently, all known algorithms for NP-complete problems require time that is super polynomial in the input size. However, it is still unknown whether there are any faster algorithms. The methods of approximation, randomization, restriction, parameterization, and heuristic are some techniques which can be applied to solve general computational problems. These methods are known to often give rise to substantially faster algorithms.